All right, well, welcome back to another video where I will be sharing, presenting Calculus 2 prep material for you guys to learn. So in the previous lesson, we had a look at the complex numbers. Although they're pretty important, learning in university level, that won't really be um, what we're going to be having a look at later on. So uh, this lesson today, we will be having a look at the integral section, which should be pretty new for anyone who's starting to learn about calculus 2 and about the integration. Okay, so the first thing that we'll actually have a look at is the area section. So we are pretty much aware that we can calculate area of such figures such as a triangle, a rectangle, circles, or even um, any other kind of shape that you want. But the same is actually not true whenever you want to find the area under the curve, right? So let's say we consider the graph of a parabola from 0 to 1. So we draw a standard parabola. And let's say that we want to find what the area under the parabola between 0 and 1. So what we actually want to find out is what is this area down here? So that's what we want to be having a look at today. So suppose we want to find the area under the curve from 0 to 1. So one way we could actually do this is to use rectangles to actually approximate the area. So once again, I'm going to draw a parabola from 0 to 1. So this is 0 to 1. And I'm going to break it up into 4 separate intervals where all the intervals are actually equal. So say I break up the interval. So let's say we have approximately a half, a quarter, and 3/4 of along the way. So that means this point here is going to be 0.25. This is going to be 0.5 here. And this point here is going to be 0.75. Now, let's say that we consider extending the rectangle to the y-axis. So, or meaning we draw the rectangle until each of the endpoints. So we're going to go to the left. Each of the point, we're going to go to the left and then go to the next one down. So go next, go down, and we're also going to go to the left and then go down here. So that's the area that we want to find out. So the question is, we have all this area. So all this area that we have here, this area is already a lot of the area that we want. So the only thing that we just have here is just the extra area, right? So let's say that, well, this height here is h1, this height here is h2, and this height here is h3, and last one being h4. So let's calculate each of the height. So the height here would just be evaluated at the function at that specific point. So that means if we want to find h1, then that means we calculate f at 0.25, which is going to be at this point over here. So that means if we put it into x squared, so that'd be 0.25 squared. That'd be 0.0625. Right, so that's for the first height. For the second height, h2, we do the same thing. So we plug in f at 0.5, which is 0.5 squared, which is going to be 0.25. H3 being f 0.05. So we have 0.75 squared, And that would equal to 0.5625. And last one, we calculate h4, which is just going to be f at 1, which is just going to be 1 squared, or equal to 1. Now, what we calculate, so we found the height of each of these. So we calculated this height, we calculated this height, we calculated this, and we also calculated this. So what's the next step here that we want to do? Well, the next step here is that we calculate the area under each of these rectangles here. So we calculate this plus this area plus this area plus this area here, right? So let's find the areas. So call it A1 to be the base multiplied by H1. So the base here, since I divided the intervals of each of between 0 and 1 equally, all the units, or the distance between 0 to 0.25 is the same as from 0.25 to 0.5, and then 0.5 to 0.75, and then 0.75 to 1. So all of them are going to be of equal distance between each other. So that means the base is all going to be 0.25. So if I put this in, so the base here, 0.25, multiplied by the height of 1, which is 0.0625. Now that is just going to equal to 0.015625. The area 2, if you do the same thing, you get 0.0625. Area 3, which is 0.140625. And A4 to be 0.25. So that is the area of all these rectangles here. So that's this area for A1. This area is for A2. This area is A3. And this area is going to be A4. Right? So what's the next step? Well, to find out what the area is, we just have to add up all the rectangles, or areas of all the rectangles. So we say that the area total would just be the sum of A1 plus A2 plus A3 plus A4. Now then, that would actually equal to 0.6875. Right? So that's an approximation of the area that we have just calculated. But if we now, so suppose we have the same parabola again, but this time we're going to be using the left strip of each of the parabolas here. Left edge of this parabola. So in the previous one, we considered the rectangles that are involving the right edge of each rectangle. But now let's see what happens if we involve the left edges now. So what that means, so once again, I'm going to divide the area, or divide the interval 0 to 1 equally between 0 and 0.1. So we have 0.25, we have 0.5, and 0.75 again. So say now, since we're going to consider the left edge of each rectangle, so that means I'm going to be considering the line down here. So notice that this point here is connected to the left strip, and similar to the other parts, I could use this strip, I use this part, and I use this part here. So each of these parts, if I just draw the diagonal, or the vertical part, that's the area that we want to calculate here. So if I calculate this area, and this area, that would be pretty much enough. Well, the first one, we also have a height of 0, which means we also have an area of 0, because it's just going to be the area of a line, which that means that the area is just going to be 0. All right. So that means if we calculate the height once again, so if we say that, well, H1, we said was 0. H2, if we calculate the area of that, or f at 0.25, then we will get 0.015625. 0.625. If we calculate H3, we would get 0.25, and H4, we would get 0.5625. And calculating the areas again, so we get A1, which is 0, A2, which is 0.015625, A3, which is 0.0625, and A4, which is 0.140625, right? So that means now the area total, if we add up all the area, so A1 plus A2 plus A3 plus A4, we will obtain 0.21875, which pretty much would not be the right. So you see that the area from the previous part, we got 0.46875 versus this one where we got 0.21875. How can we make our guess a little bit better? So can we probably average the two values that we get? So if we try to average the right edge plus the lower edge or the left edge, so let's try the average of this. So A bar, if we calculate the area of the left edge plus the area of the right edge, and we take this all divided by 2. So the left edge we said was going to be 0.21875 plus 0.41 or 46875. So that was the area that we calculated, all this divided by 2. And so if we calculate this value, what we should get is approximately about 0.34375, which is actually a pretty good approximation. But what other ways can we make our guesses a little bit better? Well, the thing here is we could actually create more intervals. So notice that in the previous part, we have this little bit of extra area that is above here, above here, above here, and above here. We don't want that area. And same thing with the other triangle here. We're missing some area here, some missing area here, this area here, and this area here. So how can we actually make that error in each of the rectangles that we create a bit smaller? Because we want it to be slightly almost exact with each other, right? Well, the answer to that is if we have more rectangles, each of the extra areas, for example, in this one, would get a lot smaller. So say if we have another rectangle here, then that means we have this, and we only have this part that would be only smaller. So let me draw this. So say we have this grid here, which I'll get a bit better. So say we have the parabola once again, and we have that. Well, if we consider the right edge rectangles, so I'm gonna try my best to create as many small rectangles as possible. So, so this part, if I draw more vertically, so if I try to make them as equal as possible, and then if I create them by considering this, okay. So we see here that as we add more rectangles to the area here, we would see that we get smaller error over here. So this smaller error is actually what's going to make the approximation a lot better. So the key thing here is that if we have more rectangles, then that means we would have the extra area will be smaller. right? So that means if I consider, well, if I draw another set of axes, and if I draw the parabola, well, if I consider slicing, well, breaking it up into infinitely many rectangles, and then if I just keep on going until maybe like here, here, until I reach the endpoint at 1. So if we have n rectangles, let's say, each of them, well, going to be a lot better than the previous approximation. So that means, so if we consider this one, so that means our approximation gets better. Approximation gets better the more rectangles we draw. Because we have a smaller extra area. Right? So that's the idea behind the area under a curve. However, if we let n represent the number of rectangles, meaning that that is going to be the number of divisions we make. So for example, once again, I'm going to draw the parabola, but the simple one this time. So if I break this up into n times, maybe even a bunch of them until here, this part, then if we let b, so we're going to let b, which is the base. So the base here, if we divide them between 0 to 1 all equally, then that means each of the bases between each of the intervals will have a base which is equal to 1 over n, right? But what is the height? So h of 1, we don't know what that is. Well, we do know that, well, x1 is going to be 1 over n, x2, which is 2 over n, and if you keep on going until the kth in value, so that'd be k over n, right? So if we find the height at each of these, well, we would attain that, well, the height of f of x1 would just be 1 divided by n squared. 1 divided by n squared. And if we calculate it at h2, x2, the height of this would be 4 divided by n squared. And if we keep on going into the kth derivative, or kth in value, we would get k squared divided by n squared, right? So the idea here is that we're using the right edge tool, right edge to find the area here. So we're talking about this part right here, right? So what is the x-coordinate of the right edge of each triangle? So that's what we want to find out. Well, let's calculate the area of each of the bases and the heights. So if we calculate the first area, A1, which is B, which is the base times height 1, this one would just be 1 over n because each of the bases have 1 over n as the base, multiply the height, which is 1 divided by n squared, which is 1 divided by n cubed. If we calculate n2, a2, same thing. So we have 1 over n by 4 divided by n squared, which is going to equal to 4 divided by n cubed. And if we keep on going with the process, by the time you get to the kth area, we see that, well, we'll get 1 over n as the base. So multiplied by k squared divided by n squared, which is just going to be k squared divided by n cubed, right? So that means if we start, well, the area here, the total area of the rectangles here, or the sum of all the areas, would just have to be based on this part. So we have A1 plus A2 plus dot 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 until area k. Or we could also write this as a sum. For example, if you want the kth one, and then we just keep on going until the nth one, right? So that means we would just have the sum here from k is equal to 1 until n. So we're going to go from 1 to n. The general kth version is just going to be given by this, right? So that means for ak, or that is also equal to the sum k is equal to 1 of k squared divided by n cubed, right? But here's the thing now. If you want to find the exact value of the area, the best thing that we could actually do here is take the limit as n approaches infinity. So if you want an exact value, we calculate the area, the limit, calculate the area of which is equal to the limit as n approaches infinity of n from k is equal to 1 of k squared divided by n to the power 3. So when we do that, well, let's find this limit. So a, which is equal to the limit as n approaches infinity. So from this step, I'm actually going to drag out the n cubed to the outside. So this is going to come out. So we have 1 divided by n cubed. And we have this notation here. This is going to be k squared. But what was one of the formulas that we have talked about in the lesson 1, which was the one that involved the summations? So going back to this one, we would actually have to be using this formula over here, right? So let me go back to the next page, the page. So that's the formula that we have here. So let's go ahead and use that formula. So we have the limit as n approaches infinity of this sum, so that just becomes, so 1 divided by n cubed, multiplied by n times n plus 1 times 2n plus 1, all this divided by 6, right? And so by expanding everything else, so let's go ahead and expand the numerator. We're also missing the limit on the outside. So the limit as n approaches infinity of 1 divided by n cubed. So that's, if we expand this, we're going to get 2n cubed plus 3n squared plus n, all of this divided by 6, right? Or if you want to, so let's expand with the 1 divided by n cubed. We would get 2 over 6 plus 1/2 divided by n. And we would also add 1 over 6n squared. Okay, so well, we could see that as n approaches infinity, this would stay as a constant. This would be approaching 0, and this would also be approaching 0 as well. So we could actually just cancel these. So that's going to 0, goes to 0. So what we're actually left with is this value over here, this 2 over 6. Well, that means the area here is going to be exactly 1/3. This here, this area here, represents the exact area under y is equal to x squared from the interval 0 to 1. And that's how we could actually approximate areas under the curves. And we could also do the same thing with other functions as well. So let's say we wish to determine the area under the curve of y equals to f of x. So what f of x is just some function that is probably that is continuous over a to b. So let's say here's a, here's b, and we divide the area once again. So say we break it up into n equal intervals, and so on until we reach here and here. And using the right edge method, we could also find the areas of this curve as well, right? So that's the method. So the idea here is that, well, if this is, let's say we call this point over here being x1, this point being x2, well, x1 here would just be a plus the width. So the width here is actually going to be determined in a bit. But if we want to find for x2, then that would just be, so this point, that'd be a multiplied by the width of this part. So starting from a, 2 times the width. And if we keep on going for maybe about n times here, or k times, so xk, if we say a plus k times the width, so that's going to be this area here, or the value at, or the coordinate at this point here. Well, if we divide the area under the graph into n rectangles of equal width, then each of the width of the rectangles can be determined as, so the width here now simply just becomes b. So we take the range of the, or the distance between b and a, so a minus, or b minus a, and we divide it by the number of rectangles that we want. So n in this case. The b minus a here is the length of the interval. Between a to b. All right. So if we use the right edge to determine the height, we need an expression for the x-coordinate. So we're actually just going to be denoting the x-coordinate by xi star, which is equal to a plus the ith coordinate, b minus a divided by n. Or more in general, we would use k, but that doesn't really matter here. But so that means x1 would just be a plus b minus a divided by 2, or n. X2 would be a plus 2 times b minus a over n, or more in general, xk here, a plus k times b minus a divided by 2, n. So that's the general formula for the kth coordinate. And also, the height could also be written as, well, h of k, the kth coordinate, that would just be f at the xk star, or f I star, whatever index you want to use. All right. And the area then will just be the sum of all the rectangles here. So we would just have the area, well, that's just going to be a1 plus a2 plus da da da, plus ak plus da 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 until the an. And that would just be the width times the area. So this is width by the area at each of the star coordinates. So this would be width times fx2 star plus dot 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 until we get the width times fx n star, which then would lead us to b minus a divided by n of f at a plus b minus a divided by n. And we have b minus a divided by n. Multiply that by f a plus 2 b times b minus a divided by n. And plus, well, we would just keep on going until we reach b minus a divided by n. Multiply that by f a plus the k b minus a divided by n, and so on. So that would be the area of all the approximations here. And now, it is more convenient to express this using the summation notation that we have talked about in lesson 1 here. So that means A, we could write this as a sum from k is equal to 1 to n of b minus a, so that's going to be the width, multiply this by fxk star, where xk star, once again, is the starting point of the interval, and you're adding k times b minus a divided by n. All right, so that's the starting point now. So we're almost there to get better at approximating areas here. Okay, so let's say we want to determine the area under the graph of y equals to x squared from 2 to 4. So let's draw a graph for this. So we have the graph from 0 to 4. So let's say this is 4 now. So that means this part here is 2. So we want to determine what this area is going to be. So this area is what we calculate. All right. So that means, so if we calculate the width first, the width here is actually just going to be equal to b minus a divided by n, which is 4 minus 2 divided by n. So each of the width here is going to be 2 divided by n. And that means each xk star is going to be given by 2 plus k times 2 over n, which is also this, well, 2k, so 2 plus 2k divided by n. So that's each of the x coordinates position. And finally, well, fk star, or fxk star here, it's just going to be 2 plus 2k divided by n squared. Or if we expand this all out, what we should get is 4 plus 8k divided by n plus 4k squared divided by n squared. All right, so we're almost done. So let's put this into the area now. So once again, the area here can be written as a sum from k is equal to 1 to n of the width. So the width here is going to be 2 over n. And each of the xk star is going to be 4 plus 8k divided by n plus 4k squared divided by n squared. Then if we distribute everything, so k is equal to 1, so we get 8 over n plus 8, so 16k divided by n squared plus 4k squared, or 8k squared, divided by n cubed. Well, let's put all this together. So 8 over n, I'm going to expand using the property for summations. So expand, expand, expand. So what we get here, and I'm also going to be bringing out the 1 over n for the first summation. So we have 8 over n for the first one, and then we have n from k is equal to 1 to n of 1, and you'll see why. So, and then we have 16 divided by n squared. So that's why I brought it out. And then we also have the sum k is equal to 1 of k. And lastly, we have 8 of n cubed. So the sum from k is equal to 1 to n of k squared. Well, we know what each of the formulas are because those are from the ones that we have talked about in lesson 1. Those are all the 4 formulas that we need. So we need this formula, we need this formula, and we need this formula here. So those are the 3 formulas that we need. And so let's go ahead and put those in. So we have 8 divided by n multiplied by n, And then we have 16 divided by n squared. This sum of k natural numbers is going to be n times n plus 1 divided by 2. And then we have 8 divided by n cubed. Multiply that by n times n plus 1, 2n plus 1, all divided by 6. Well, that means here the 8 will cancel out. The n's here will cancel out, so we get 8. By expanding the first one, we should be getting, okay, so we get, so 16 divided by n squared, multiplied by n squared plus n, divided by 2, and then 8 n cubed. Or actually, I'm going to come and factor out the 8 here, or the 2, so that this becomes 8 and 1. This one becomes 4 over 3. And we would just have 2n cubed plus 3n squared plus n, right? All right, so let's go ahead and take the limit as n approaches infinity now. So here, what we actually have now, well, so actually not just yet. So we still have the 8 divided by n squared. I'm going to common factor out the n squared here. So that I would just be working with 1 divided by n divided by 1. Well, let's leave it like that. And same thing here. I'm going to common factor out the n cube here. So that we have 2 plus 3 divided by n plus 1 divided by n squared. Now, because when I do this, I could actually easily cancel out some terms. This cancels with that. So that means what I just need to find out is this 1. 4 over 3 multiplied by 2 plus 3 over n plus 1 divided by n squared. So now if I take the limit as n approaches infinity, so we get an exact value, we get, well, 8 times 1 plus 1 over n, 4 over 3, 2 plus 3 over n, 1 divided by n squared. So we see that any of the rational numbers will just go to 0. So this is going to go to 0. This is going to go to 0. This is also going to go to 0. So what we're actually just left with is just going to be this value, and this value multiplied by the 2. So we would just be left with 8 plus 8 plus 8 over 3. And if you calculate this, this is exactly 56 divided by 3. And that is the area under the curve of y equals to x squared between x equals to 2 to x is equal to 4. All right, so now let's have a look at the next part. Well, the limit of the sum that we have defined earlier is simply just going to be the definite integral of f from a to b. And so we could write this as the limit as n approaches infinity of the sum from k is equal to 1 to n of b minus a divided by n of f of xk star. Well, we're actually going to use a little a notation here. So this b minus a divided by n, we're actually going to denote it by delta x, which is the width. All right. So when we take the limit as n approaches infinity, so I'm going to rewrite this as the limit n approaches infinity, the sum from k is equal to 1 to n of f of xk star multiplied by each delta x. That is actually going to be equal to the integral from a to b of f of x d of x. So the parts of this integral here, so we finally establish a regular form of the integral, or the definite integral form of f. So this is the b to a is simply just going to be our interval. The integral sign here is going to be our sum. The f of x is always going to be our height. And this dx is going to be representing the width of the function or the interval. So if the limit exists, then we say that f is integrable on a to b. So this expression gives us a way to determine area under a graph by dividing into subintervals, or a partition, if we would like to say it as. So if the graph is above the x-axis, the area will be positive, or if the graph is below the x-axis, it will give a negative area. So if we therefore take the definite integral of the function that has parts above and below the function, it would give us the difference between the areas, where some of them are going to be the positive and some of them are going to be on the negative side. So for example, if we take the area of, if you want to find the area of the function x squared minus 1 from 0 to 2, well, that's just meaning that we're going to have to find this integral. So we calculate the integral from 0 to 2 of x squared minus 1 of d of x, but we haven't exactly went over how to actually calculate the integrals, which will come later on. So we're going to be going back a little, and we're actually going to be calculating using the regular way, which is the limit as n approaches infinity of the series from k is equal to 1 to n of f of x k star multiplied by delta x, where delta x here is actually just going to be 2 over n, and the xk star coordinate is just going to be 0 plus k b minus a divided by n, or 2 over n. So that's just going to be 2k divided by n. All right. So now that means fk x star, now xk x star, xk star is just going to be, so that's 2k divided by n squared minus 1, or 4k squared divided by n squared minus 1, right? So we just use the summation technique similarly how we done it before. So that means the limit as n approaches infinity of the sum between k is equal to 1 to n of the function, which is 4k squared divided by n squared minus 1, multiplied by the width, which is 2k 2 divided by n. So divided by n. So that is also the same as saying the limit as n approaches infinity of the sum k is equal to 1 to n of 8k squared minus n cubed minus 2 over n. And this is also the same if we rewrite this a little. So one of them we would have, for the first one, we have 8 divided by n squared, or n cubed, multiplied by the sum from n is equal to, k is equal to 1 to n of k squared. And then we subtract it by, well, I'm going to bring out the 2 over n, multiplied by the sum from k is equal to 1 to n of 1. So by calculating this value, we would use the summation formulas. So limit as n approaches infinity So for the first one, we have 8 divided by n cubed, multiplied by n times n plus 1, 2n plus 1, divided by 6, minus 2 divided by n times n. Or simply that would just be equal to 8. So the limit n approaching infinity of 8 divided by n cubed, multiply that by 2n cubed plus 3n squared plus n divided by 6 minus 2. So if we take the limit on both sides, or of this entire thing, what we would just get is just 8 over 3 divided by 2, which is just equal to 2 over 3. And that is the area between 0 to 2 of the function x squared minus 1. So visually, this is what it would look like. So if we have the function, well, let me draw a better scale. So we have the function that looks like this, between 0 and 2. So this point is going to be 1, and here's 0. So we have some of the area that is going to be in the red zone here, while the other area we'll have is on the green zone, which represents the positive area for the green. So this represents the positive area. And this down here represents the negative area. All right. So let's go on to the properties of the integral, definite integral. All right. So since the definite integral is based on the summation notation, it would have similar properties. Okay, so let's have a look at these properties. For the first property, we have that, well, if we have the integral from a to b of a constant times dx, that would just be the area of the function c multiplied by b minus a. So that means visually, if you have an integral from a to b, so here's a, here's b, you have a constant function c, it would just be the area of the rectangle where the base is just going to be b minus a, and the height would just be the c here. So that's just simply just going to be the area of a rectangle. All right, so that's the first property. The second property is, well, if we have the integral of f of x plus g of x, or minus g of x, which I'll talk about. This is, in dx here, this is also the same as saying the area, the integral from a to b of f of x dx, plus the integral of a to b of g of x d of x. So that means you're finding the area of one function, and you're also finding the area of another function, g of x, d of x. All right. The third property here that we would have a look at is that if we have the integral from a to b of a constant multiplied by the function f of x times d of x, then this is also the same as saying, well, c, the constant, times the integral from a to b of f of x dx. Okay. And property number 4 will have that, well, if we have the integral from the a to b of f of x minus g of x dx, then that would just be the area from a to b of f of x dx minus the area of a to b of g of x d of x. All right. So the next step for the fifth one, now this sort of follows from the summation part, which you'll probably be familiar with. If you have the integral from a to c of f of x dx plus the area from c to b of f of x d of x, this is also the same as saying, well, the area from A to B of f of x d of x. Okay. Now, for the sixth property, if we say, so if f of x is greater or equal to 0 for all x in AB, then that means the area under A to B will also be positive as well. Okay, so that's the sixth property. And the seventh property here, we have that, well, if f of x is greater or equal to g of x for all x in AB, then the area of f of x will be greater than the area of g of x. So the area from A to B, f of x d of x, will be greater or equal than the area between A and B of g of x dx. Okay, so let's say if f is bounded above by m, bounded below by m, but it's also bounded above by m for f of x in AB, or for x in AB. So meaning that, well, if you have a function that looks like this is the upper bound, this is the lower bound, the function is going to stay within this range here. Then we say that, well, the integral or the area under the lower bound, which is a constant, is going to be less than or equal than the area from A to B, f of x at d of x, less than or equal to the upper bound multiplied by b minus a, which is another constant function. So this property is also true. And the ninth property, well, this one should be easy to explain. Well, if we have the integral from a to a of f of x d of x, no matter what, that's just going to equal to 0. That is because we're taking area of a line. So if we say, well, if we have some function that looks like this, we want to know what this area is. We have an area of a line. There's no width between A here. So that means if there's no width, it's going to be 0. Therefore, the area is going to be 0 as well, right? So now, the last property, if we have an integral from A to B of f of x dx, this is also the same as saying the negative integral b to a of f of x dx. So those are the 10 properties of integrals that we will be keeping in mind for now. Okay. So that's for the area section. So there are two theorems that we will be having a look at that will be pretty important. So for the first one, we'll be having a look at the extreme value theorem and the squeeze theorem as well. So the extreme values theorem says, if f is continuous on AB, then there exists two numbers u, v in AB, such that if f of u is equal to m and f of v is equal to m, where m and m big M are the absolute extrema of f of AB. So what that means, if we have a function that we draw like this, so say we draw a function that looks like this. This part over here is going to be the m. And this function is going to be the m here. So the function, we say that it's also bounded above by m here, although it's not really exactly. Let me try to fix that. There we go. So that's m. And we also have this lower bound, m here. So we're saying that the function will always be between these two lines here. So this function is between a to b. So a to b is here. So b here, a is here. So that means there's going to be 2 points where there's going to be the absolute minimum and maximum values. So this m here represents the absolute maximum. And this m here, which could be over here, represents the absolute minimum of the function on the interval EB. All right. And one more important result is called the squeeze theorem. So we say that if f of x is less than or equal to g of x is less than or equal to h of x, when x is approaching a, and if, so we say that if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x is equal to some number L, then that means the conclusion here is that the limit as x approaches a of g of x will also equal to L. So visually, how this would actually look like is that we have the graph here. Say we have one function that goes somewhat like this. Let's say that's going to be the upper function, which is our h of x. Say we have another function that's going to go somewhat like down here. That's going to be our f of x. And say that we have a third function that looks like that. But so if this is the point A here, so I'm going to denote this point as A, then the limit here is actually going to be L. So we see that as x is approaching A here, is going to approach this L here, this L line. As it's going this way, same thing, this one here and this one here. So that means, so this h of x here, so we can say that we can find this limit as x approaches a. So usually you would have a function, if you're given a function where you want to evaluate where it's approaching, but the function is not that easy to find out where it's actually approaching. So that's where the squeeze theorem comes in. So if the green function represents g of x, this limit over here, so this is for this one. For this one, we cannot easily find this limit. This limit, but the function f of x, we can find this limit. So here's an example of the squeeze theorem. Say we want to find out what the limit as x approaches 0 of x squared cosine of 1 over x. But if we do a direct substitution, that's going to give us some problems here. Because if we put 0 here into here, we get 1 over 0, which does not exist then. So that's where the squeeze theorem comes in. Now note that here, cosine of anything, 1 divided by x here, is always going to be between -1 and 1, right? Well, if we multiply both sides by x squared, then that means we have x squared less than or equal to x squared times cosine 1 over x less than or equal to x squared. And so we have to condition that the f of x, so f of x here is going to be the negative x squared. G of x is going to be between x squared times so the g of x is going to be x squared times cosine of 1 over x. And h of x is just going to be the x squared here. So now we have that condition satisfied. We also see that as the limit as x approaches 0 of negative x squared and x squared, they're both going to be going to 0. So therefore, we could actually conclude that this limit equal to 0. So because we have that the limit as x approaches 0, x squared is equal to the limit as x approaches 0 of negative x squared is equal to 0. So with these two conditions here, we have condition 1 being this, the second condition being that the limits are the same. So therefore, the conclusion is that, well, this limit is just going to go equal to 0. So that's the squeeze theorem. It's very interesting. All right, so now let's say we have a function g of x that is the area of y equals to t, which is the linear function from 0 to x. So meaning that we have this function between some x here that we will have to find out. So we want to know what this area is. This is y is equal to t. So the g of x here actually represents our area. Then that means g of x can be written as the integral from 0 to x of ft dt. So that means if we compute g0, g1, g2, g3, and g4, and then graph y equals to g of x, well, let's find the values. So we have g0, which is the integral from 0 to 0 of ft dt, or since this is actually just going to be t dt, or so that means the integral here, t dt, that's just going to be half of t, or 0 by 0, which is going to be give you an area of 0, and that's by one of the properties that we have talked about by property number 9. So by property 9. Okay, so that's g of 1. Well, g1 or g of 0 from the last one, we calculate from 0 to 1 of t dt. Well, we do the same thing. This is simply just going to be the area of the triangle up here, or area of this triangle here. So we have the base, which is 0 plus 1 divided by 2, which is a half. The base is 1. And then the height would also be determined as well. So that means we have a half times 1 times 1 as well. So that's going to give you 1/2. So if you think about the area of a triangle, this is between 0 and 2 or 1 x. And the height here would just be f x here. Or y, yeah. Now, g2, we do the same thing. So from 0 to 2 of t dt, we get half 2 by 2, which is equal to 2. So the length here is now going to be 2, and the height would also be 2 as well at this point. Now g3, if we do the same thing, this is just going to be 9 over 2, and then g4 is then just going to be 8. Now let's plot this on the curve now. These values should look pretty familiar. Okay, so if we, so 2, 4, and if I say, so 2, 4, 6, and 8, well, let's put these all in here. So g0, which is 0, G of 1 we said was a half, so that's going to be about here. G2 is going to be 2. G3 is going to be 9 over 2. So that's about 4.5. No, that's going to be slightly below. So here. And then G of 4 is going to be 8. Well, guess what? This is exactly a parabola that we have just constructed. So this is between 0 and 4. We have found a parabola. So this is a parabola. Very nice here. So this is a good observation. So that is what the fundamental theorem of calculus is saying. So the fundamental theorem of calculus here says that if f is continuous on a to b and g is a function defined by g of x is equal to the integral from a to x of ft dt, where x is between a and b, then g here we say is also continuous on ab. It's differentiable on the open interval a to b, and g prime is equal to f. So visually, we could see that, well, if we construct two curves, so say we have this curve. So here's A, here's X, and this is B. So we have one area that's this part over here. So that area is going to be your G here. And similarly, if we have some small increment to the area, or to the length, to the X here. So say we have this part, but this part here now is going to be our X plus H instead. Here's B, here's A. This is going to be the area of A to X plus H. So we're calculating the small incremented area. So area, which is G of X plus H then. Now, if we take the difference between the two then, so that means G of X plus H minus G of X, obviously the larger area will be first. Then that means if we draw the combined graph of this, we would have something that looks like this. So if you have this graph, you have A, let's say this is X here, this is the X plus H, and then this is B. So that means, so I'm going to use different colors for this. For the first area, let's say we have the area of G of X plus H given by this here. So this is what we have for the first part. And if we take the area of the smaller part between X to X plus H, so that'd be the area of this small portion here, then that means what we're just going to be left with, it's just going to be this portion of the area. So this small portion on the graph here is this exact difference over here. That's the difference in area. So that means for this part here, we can approximate this area with a rectangle as H approaches 0. So that means X plus H is going to approach X, and f of X plus H is going to approach f of X as H approaches 0. So that means if we have that the limit as H approaches 0, f of X plus H, which is f of X, then that means we have the limit as H approaches 0 of G of X plus H minus G of X, which is also equal to the limit as H approaches 0 of f of X by H. well, if we divide both sides by h now, so that means we'll have the limit as h approaches 0, g of x plus h minus g of x, this divided by h, then that means we have the limit as h approaches 0 of f of x. So because this is simply just, this side is going to be a constant, so that's going to be f of x. On the right-hand side, however, this is simply the definition of the derivative. So that's going to be g prime of x then, right? So we have g prime, and the right-hand side simply just becomes f of x. So that's where the third condition of Fundamental Theorem of Calculus part 1 comes in, which is this part over here. So that's the Fundamental Theorem of Calculus. So let's have a look at some examples now. So let's say we want to determine the derivative of the following functions. Well, for the first one, let's say we have from 2 to x of 2t cubed of dt. Well, g prime of x then would simply just be, well, d over dx times the integral from 2 to x of 2t cubed dt. But this would simply just be 2x cubed, because we said that the derivative of g, so this derivative, would be the same as the original function f of x. So our function here would then be our 2x cubed. Because g of x, we defined it as a function of f of t. So we have an f of t here. We would just replace it with the x, and that would give you the result. Okay. So let's have a look at the next part. So we would see here that, well, h of x here, we have the integral from x to 4 of t minus 3, but we could also rewrite this a little, remembering that, well, if we use property number 10, we would have the integral from 4 to x, but we have the negative on the outside, so that'd be t minus 3 dt. Now we take the derivative on both sides, so we say that, well, h prime of x is equal to, so the derivative of 4 to x of t minus 3 dt. Well, this is going to be our f of t, so all we just have to do is replace the f of t with f of x instead. So, and then the integral will also be canceled out. So that means this would just be equal to x minus 3, the square root of it. Right? And one more example. We have p of x, which is the integral from -4 to x squared. So this is going to be a little bit trickier. Then we would have 2t of the function 2t minus 4 cubed of dt. Then the integral, the derivative of this. So if we take d over dx between -4 and x squared, 2t minus 4 cubed dt. So now we're actually going to be replacing the x. So instead of ft, so that means we're actually going to be replacing with fx squared instead. So this is also important here. If we have some other function rather than just x, then we would also have to substitute this x squared into in here. So what that means, we would just have 2x squared minus 4 cubed. And by the chain rule, we also had to take the derivative of x squared, which is just going to be 2 times x. And that is for the Fundamental Theorem of Calculus part 1. All right. So now let's have a look at the Fundamental Theorem of Calculus part 2. So this theorem states that, well, if you have a function f that is continuous on AB, and f is the antiderivative of AB. So this is where antiderivative will come from. Where f is any antiderivative of f, then we say that, well, f prime is equal to the function f, and we also get this result of the integral from a to b of f of x dx, which is the antiderivative from b and the subtract that from the antiderivative of a, right? So let's have a look at these examples. So say if we want to find the area under each of these curves here from 0 to 1. Then, so let's find the area. So we say, well, the area from 0 to 1 of x squared dx, remembering that the antiderivative of x squared is simply, so if we have x to the power n, this is going to be 1 divided by n plus 1, x n plus 1. So since n here is going to be 2, we're going to have 1 over 3. So that's 1 over 3 minus, or x to the power 3, between 0 and 1. But you might be asking, well, what happens to the constant in this case? Well, the constant here actually will not really matter in this problem here, because the constants will always cancel out with each other. So that's why the constants are not going to be necessary whenever you're evaluating any definite integrals. But whenever you're evaluating indefinite integrals, which will come in the next lesson, you would always have to keep the plus c there. All right. So that means we're actually evaluating this antiderivative at f1 minus f at 0. So these two notations are pretty much the same. So that means if we have 1 cubed, or 1 over 3, times 1 cubed, minus 1 over 3 times 0 cubed. So that means the area here would just be 1 over 3. Now this area that we have found is also the same as the one that we approximated earlier on this page here. So we calculated the same area, 1/3, by calculating the area between 0 and 1. But this is by using this long process, which will not be really necessary no longer, because we have integrals now, so definite integrals, so that makes it a lot easier to calculate. And so for the last part, let's have a look at this one. So if you want to calculate the area of this, well, this is just going to be the area integral from 0 to 1, ex dx. The antiderivative of e to the power of x is e to the power of x, so that's just going to be so f at 1 minus f at 0. So e1 minus e0, so that's just going to be e1, or just e minus 1, which is that area. Okay, so I think we'll take a pause here. So the next lesson, so we stopped with the fundamental theorem of calculus. The next session, or the next lesson, we'll actually be continuing on with the definite integrals before we actually proceed on with any other stronger techniques of integration. All right, so if you guys have any questions, just feel free to let me know in the comments.